Hey there! In this video, I will show you how to formally prove a sequence diverges to infinity using the appropriate definition. I say appropriate because it's a definition that one can use to prove a sequence diverges to positive infinity, and one specifically for a sequence that diverges to negative infinity. For our purpose, we will use the positive infinity of definition since what we want to show here is that if we let r be greater than 1, we want to prove that the limit as n approaches to infinity, the sequence r raised to the n is equal to positive infinity. And the definition we will work with is as follows. A sequence, a sub n, of real numbers is said to diverge to positive infinity provided that for all real numbers, capital M, there exists a natural number, capital N, such that for all little n greater than or equal to capital N, the sequence a sub n is strictly greater than m. So let's take a closer look at our definition. Note the order of our quantifiers. We are given a capital M, so the capital N that we have to find may depend on this capital M. So let's begin looking for our capital N by doing some side work. We do that by working our way backwards through the definition we are given to find a capital N that works. So notice we have the sequence r raised to the m is greater than m. And what we want to do is isolate this little n on the greater than side of the inequality. So our first step is taking the natural log on both sides. And this will allow us to bring this n down. Next, we can divide both sides of the inequality by this ln of r in order to isolate this n. Now, we might feel that we have found our capital N since the little n is on the right greater than side of the inequality. But notice that the natural log of a real number m divided by the natural log of a value r that is strictly greater than 1 is likely not a natural number. So let's take this expression and apply it into the greatest integer function. So for now, our choice of n is and what this does is ensure that we don't get a decimal number for our value of n. And the next thing we could do is raise our value of n to the second power. And what this does is prevent n from being a negative number, as negative numbers are not natural numbers. And in order to prevent 0, we could just add a 1, since 0 is not a natural number. Now that we found our natural number n, let's begin our proof. We open our proof by introducing the capital M. We then move on to stating our choice of the natural number n. And now we want to satisfy the last part of the definition. So we write then for any natural number little n greater than or equal to n, we want to show that the sequence r raised to the m is greater than capital M. And since little n is greater than or equal to capital N, and capital N, we could claim, is greater than the natural log of big M divided by the natural log of r, it follows through this chain of inequalities that little n is greater than the natural log of m divided by the natural log of r. So notice that n greater than m divided by the natural log of r. We divide both sides by the ln of r. We then exponentiate both sides to allow this n to be moved back to this r. which simplifies to Rn is greater than m. And this is what we wanted to show. Hence, if r is greater than 1, then the limit as n approaches to infinity of the sequence r to the n is equal to positive infinity. I hope this video has been helpful. Thank you for watching.